Peru's greatest mystery may finally be solved, and the ruins are even stranger than we thought. Somewhere in the Peruvian Andes, there is a wall you can press a knife against, and it will not go in. Not a millimeter. Not the width of a single hair. Stones the size of delivery trucks, some heavier than a school bus packed with children, sit locked against each other with no mortar, no cement, no gap at all. People have spent their entire careers trying to explain that wall, and for 500 years, nobody has fully succeeded. But that may be changing right now because in just the last few years, laser scanners, mineral testing, and old-fashioned stubborn fieldwork have started pulling back the curtain on how these stones actually got here. And what they're finding is not aliens. It's something almost more unsettling, a level of human skill so advanced, so quietly confident, that it makes the story we were taught in school look incomplete. Let's start with a place most people have actually heard of, even if they don't know its name. Sacsayhuamán, perched on a ridge above the old Inca capital of Cusco. From a distance, it looks like three enormous stone waves frozen mid-crash, zigzagging across the hillside. Up close, it stops being pretty and starts being frightening, in the best possible way. Some of the blocks in that wall are estimated to weigh well over 100 tons. To put that in perspective, that's heavier than a fully loaded 18-wheeler, heavier than an adult blue whale. And these aren't just piled on top of each other like a rock garden. Each block has been shaped to hug its neighbors, curved edge fitting into curved edge, corners tucked into corners, the whole thing locking together like a three-dimensional jigsaw puzzle carved from solid stone. Engineers and stonemasons who visit today still crouch down and run their fingers along the seams, half expecting to find a crack, and instead they find a joint so tight it feels almost welded. Here's the detail that turns this from impressive into genuinely strange. Cusco sits in one of the most earthquake-prone regions on the entire planet. Over the centuries, the valley has been hit again and again by powerful quakes that leveled colonial-era buildings, churches, bell towers, stone facades built by European masons using the best engineering Renaissance Europe had to offer. Those structures cracked and collapsed. Meanwhile, the older walls at Sacsayhuamán, built with no iron tools and no written mathematics that we know of, absorbed the shaking and stayed standing. Some structural engineers who've studied the site believe the trapezoidal shapes and the tightly interlocked joints act almost like a built-in shock absorber, letting the wall flex slightly during a quake instead of shattering. Whether that was deliberate design or a fortunate side effect of how the stones were fitted is still debated. But the outcome isn't in dispute. The primitive wall outlasted the advanced one, over and over again, for 5 centuries. Now travel down into the Sacred Valley, to a site called Ollantaytambo, and the mystery gets a second, heavier layer. This is a fortress temple built into the side of a mountain, and to reach the top, you climb a staircase steep enough that most visitors stop halfway up just to catch their breath in the thin air. At the summit stand 6 massive slabs of pinkish stone, each one taller than a 2-story house, each estimated to weigh somewhere between 50 and 80 tons. They stand upright, shoulder to shoulder, their faces polished smooth, with thin strips of stone fitted between them almost like spacers in a modern construction joint. Here's what should stop you in your tracks. Those slabs weren't quarried anywhere near where they stand. The stone came from a quarry on a completely different mountain several miles away, across a valley. To get the blocks from that quarry to the temple, they had to be moved down one mountainside, across the valley floor, over the Urubamba River, and then up the steep face of a second mountain. Modern engineers who've modeled that route say that moving a single 70-ton block along it today would require cranes, reinforced roads, and heavy steel cable. The people who moved these stones had none of that. No wheeled vehicles capable of bearing that kind of weight have been found from this culture. No draft animal strong enough. Llamas, the largest animal available in the region, can carry maybe 80 pounds before they simply refuse to move. And yet the stones made the journey. We actually have physical proof of how hard that journey was, because not every stone made it. Scattered along the presumed route, between the quarry and the river, lie a series of massive blocks that were apparently abandoned mid-transport. Locals call them the tired stones. They sit at odd angles in the grass, some tipped on their sides, clearly on their way somewhere before the effort stopped, for reasons nobody has been able to pin down. Archaeologists' best explanation is large-scale labor. Thousands of workers using earthen ramps, plant fiber ropes, and log rollers, coordinated across months or years. That kind of massive coordinated effort is well documented in other ancient societies, and it's not fantasy. Humans really can move extraordinary weights with enough organization and enough hands. But even that explanation leaves real, unresolved gaps. No trace of the enormous ramps such a method would have required has been found, and nobody has fully explained how a rope and roller team would have safely managed a 70-ton block on the final steep ascent without it sliding straight back down onto the people pulling it. Then there's the toolmark problem, and this is where things get genuinely puzzling even to specialists. Some of the joints at Ollantaytambo show long, straight, perfectly parallel grooves cut into the stone, clean, even, consistent in depth, more like something drawn with a steady, powerful tool than hammered out with hand pounding. And the stone itself, andesite and diorite, is extremely hard, ranking close to the top of the mineral hardness scale, not far below diamond. Bronze and copper, the metals we know this culture worked with, are far too soft to cut that kind of stone efficiently. You'd wear the tool down to nothing long before you made a dent in the rock. So how are these surfaces finished so cleanly? The honest answer from most archaeologists is a combination of things. Harder hammerstones made of even tougher rock like quartzite, used to pound and abrade rather than slice, enormous amounts of time, and possibly techniques we haven't fully reconstructed yet. It's not a solved problem. It's an open one, and reputable researchers say so plainly instead of pretending otherwise. Climb even higher and you reach the site everyone recognizes on sight, Machu Picchu, balanced on a narrow ridge nearly 8,000 feet up, with the peak of Huayna Picchu rising behind it and clouds drifting through the ruins like something alive. Most visitors come for the postcard view. Almost none of them realize that the real engineering marvel of Machu Picchu isn't what you can see, it's what's buried underneath. The site sits directly on top of two geological fault lines, in a region hit by both frequent earthquakes and violent seasonal rainstorms that can dump huge amounts of water onto the slope in a matter of hours. By any modern logic, this location should be a disaster waiting to happen, a landslide risk, not a place to build a city meant to last. And yet it has lasted. The reason is underground. Researchers studying the site have found that roughly 60% of the construction at Machu Picchu is invisible from the surface. A carefully layered drainage system built beneath the terraces, with coarse stone and gravel at the base, finer gravel above that, then sand, then rich soil for planting on top. This wasn't random fill. It was engineered so that when heavy rain hit, water would soak straight down through the layers and drain safely away from the mountainside instead of pooling and dragging the terraces downhill. The people who designed this understood, without modern instruments, exactly how water behaves inside a slope and how to defeat the very forces that should have destroyed this city centuries ago. That same understanding shows up in the water system that once supplied the city. A spring high on the mountain feeds a channel that runs down through the site, splitting into a series of 16 carved stone fountains, one feeding into the next, each drop precisely calculated, so the water flows smoothly without overflowing or running dry. And here's the detail that quietly amazes hydrologists who study it. That channel still works today. 500 years after the site was abandoned, spring water still runs down through the same stone channels into the same fountains, without ever having been rebuilt or repaired. And then, once again, there's the stonework itself. In the finest buildings at Machu Picchu, the temples, the sacred enclosures, the walls are built from blocks so precisely fitted that generations of visitors have tried the same experiment with the same result. Try to slide a knife blade, a piece of paper, even a single strand of hair into the seam between two stones, and you can't do it. To achieve that kind of fit, you can't simply carve a block to a fixed plan and drop it into place. Each stone has to be custom-shaped to match every bump and hollow of every neighboring stone in 3 dimensions, and every time you adjust one face, it can throw off the fit against the stones around it, turning it into a puzzle that compounds on itself. Today, that kind of precision fitting is usually solved with laser scanners and computer modeling. These builders solved it, as far as we can tell, with stone hammers, patient trial and error, and an extraordinary eye for 3-dimensional geometry, while working on the edge of a mountain, where dropping a block could mean losing it, or a worker, over a 1,000-foot drop. Put these three sites side by side, and a pattern starts to emerge that's bigger than any one wall. It isn't just that the stones are large. It's the specific, repeated combination of traits. The hardest stone available, shaped with a precision that looks almost soft, joints tighter than most modern construction tolerances, drainage and water systems engineered for problems, earthquakes, floods, erosion, that would still challenge us today. This doesn't look like a culture stumbling toward competence. It looks like a mature, confident engineering tradition, applied consistently across multiple sites and, in some cases, multiple centuries. Which raises the question people can't leave alone. Who actually built the oldest, most precise layers of these walls? Here's something that often gets left out of the popular retellings. When Spanish chroniclers asked the Inca who built the largest, most perfectly fitted stones at sites like Sacsayhuamán, the answers they recorded were often vague or deferential. Many Inca structures show clear evidence of Inca-era construction stacked on top of older foundations, and in places the masonry style visibly changes between the lower, more massive, more precisely fitted courses and the smaller, tidier stones above them, which are more confidently attributed to Inca builders. This has led a number of archaeologists to seriously consider that at least some sites in the region may incorporate construction from an earlier period than the Inca Empire itself, possibly reworked, expanded, and built upon by the Inca rather than built from scratch by them. That's a real, ongoing area of archaeological investigation, not a settled fact, but not a fringe idea either. It's worth pausing here to be honest about the parts of this story that are colorful but not well supported. There's a long-standing legend, told in various forms across the Andes and into the Amazon, about a plant whose sap could soften stone. The idea being that a small bird uses it to hollow out nests in solid rock, and that ancient builders used the same substance to work stone by hand before it hardened again. It's a genuinely fascinating piece of folklore, and it's been repeated by explorers going back over a century. But no laboratory has ever isolated such a plant, and there is no known chemistry, no ordinary botanical compound, capable of softening diorite or andesite at room temperature the way the legend describes. Real chemical or thermal alteration of stone that hard would require intense heat or aggressive acids, industrial-scale processes that would leave clear physical traces we simply don't find at these sites. So the honest position isn't this proves a lost technology, and it isn't this is nonsense and should be ignored either. It's that we have a persistent piece of oral tradition and a stubborn, unexplained set of tool marks, and right now nobody has connected them with hard evidence. That gap is exactly where real scientific curiosity belongs, and it's why serious researchers keep testing new methods rather than declaring the case closed in either direction. This is also where recent technology has actually moved the needle, rather than just adding more speculation. Airborne laser scanning, known as LiDAR, has let researchers strip away dense jungle canopy in parts of the Andes and Amazon and reveal buried terraces, roads, and structures that were completely invisible from the ground, sometimes stretching for miles. Portable spectrometers and other mineral testing tools have let scientists examine stone surfaces without damaging them, looking for evidence of heat exposure or chemical alteration rather than relying on guesswork. And digital modeling of quarry sites, transport routes, and construction sequences has let engineers actually stress test old theories about ramps, ropes, and labor requirements against real physics, instead of just repeating them because they sound plausible. Some of these studies have supported the traditional labor and ingenuity explanation. Others have deepened the mystery, showing that certain proposed methods genuinely don't add up on paper. That's what real science looks like. Not a single dramatic reveal, but a slow tightening of what we can and can't claim with confidence. So, where does that leave us? Not with a neat, satisfying answer. And honestly, that might be the most interesting part of this whole story. What the evidence supports is a sophisticated Andean engineering tradition, one that understood stone, water, and seismic stress at a level that took the rest of the world centuries to formally catch up to, achieved with organized labor, accumulated generational knowledge, and tools that were simpler than ours but applied with extraordinary skill and patience. What the evidence does not support is any need for outside intervention, and reputable archaeologists are careful to say so. The real story isn't that ancient people had secrets we'll never understand. It's that we've consistently underestimated how much a determined, organized society can achieve without the technology we assume is required. And every new laser scan, every new mineral test keeps closing that gap between impossible and simply extraordinary. Stand in front of one of these walls, even just in your imagination, and run your hand along a seam you can't slip a knife into. That feeling, the one that makes your stomach drop a little, isn't evidence of magic. It's evidence of how much we still have to learn about what people were actually capable of, thousands of years before any of us were born. The mystery was never really about who stacked the stones. It's about how much genuine human genius can get erased by earthquakes, conquest, and time, and how much of it we're only now, slowly, starting to read back out of the rock itself. If this kind of deep dive into the world's most stubborn archaeological mysteries is something you want more of, let me know in the comments which ancient site you want covered next, and consider subscribing so you don't miss it.